Chapter 15b, Solving Equilibrium Problems. In this video, we will be learning general techniques for solving equilibrium problems, techniques that will be used both in this chapter and in the next one on ionic equilibrium. Since it is very important for you to be an active rather than passive learner, I recommend that you try to do the problems yourself before you watch my solutions to the problems. That is a more effective strategy than simply passively watching the video. All right, now what is the equilibrium concentration of hydrogen for the reaction 2H2S yields 2H2 plus S2 if initially 0.45 moles of H2S gas completely fills a 3-liter flask? This reaction is run at 700 degrees C, and the Q is 9.3 times 10 to the minus 8. So what I want you to do, if you have any idea how to do this problem, I want you to pause your playback and do it, and then come back to the video. All right, so let's first figure out, remember that in our grid we're going to put molarity, not moles, but moles per liter. So the first thing we need to do is figure molarity. We have 0.45 moles, 3 liters, that's 0.15 molar. And now we can fill out our initial reaction equilibrium grid. We start with initial concentration of 0.15 for the H2S, the reagent. We don't have any H2 or S2. Right away we know the reaction has to shift toward the product side because we don't have any product in there. And so in terms of what part of H2S reacts, we use X, an algebraic expression. And we say minus 2X will react of the H2. In other words, you have 0.15, and of that, 2X reacts or diminishes that concentration. And when we're done at equilibrium, the molarity of the H2S is going to be 0.15 minus 2X. For the hydrogen, we're initially at 0. We create 2X of the hydrogen. And how do we know we do that? Because it's a 2-to-2 or 1-to-1 mole relationship. This second line must follow the stoichiometry proportions of the balanced equation. So if this is 2-to-2-to-1, down here this line must be 2-to-2-to-1. So this is plus 2X, the sulfur is plus X, and therefore at equilibrium we have 0.15 minus 2X plus 2X and plus X. Okay, so here is our mass action expression that we write. Products over reagents to the power of their coefficients, and that is going to equal the K value, 9.3 times 10 to the minus 8. And therefore we can plug in our equilibrium values now. 2X for the hydrogen, but that has to be squared. The sulfur is X, and the H2S we know is going to be squared because there's a 2 in front of it in the balanced equation. That's going to be 0.15 minus 2X squared. So here it is. Now this is a nasty quadratic equation. And is there a way to simplify it so we don't have to go through an entire quadratic equation to get the value of X? What we're going to say is that because K is very, very small, that means very, very little of the H2S reacts. And we're saying X is the amount of H2S that reacts. Therefore, we know, because K is such a small number, 10 to the minus 8, that X is also going to be a very, very small number. It has to be. Most of the H2S is going to remain close to 0.15 molar, just a little bit less. The amount of H2S that reacts and turns to hydrogen and sulfur is very small. So compared to 0.15, even double the amount of X subtracted from 0.15 is going to be approximately the same as 0.15. We make an approximation that because X is so small, our initial concentration does not change very much or changes negligibly. So we get rid of our quadratic equation by doing this simplification. Now the problem is really easy to handle. It's going to be 4x cubed, right? 2x squared is 4x squared times x is 4x cubed divided by 0.15 squared equals the Kc value. And so all we have to do is take the cube root of this value after we multiply 0.15 squared by 9.3 times 10 to the minus 8. We now know x is 5.2 times 10 to the minus 10. And here's a mistake people make. They stop when they get to x. But please don't do that. Read the question. The question is asking for the equilibrium concentration of hydrogen. And x is not that. X is double that. That's how we have defined x and hydrogen as 2x. Right? That is the equilibrium concentration of the hydrogen. So 2x is the concentration of the H2, and that's 1.5 times 10 to the minus 9. A really, really small number. Okay? So that's how you do this algebraically, by making this really nice approximation. And most of the problems you're going to have in this class are going to be able to use the approximation. But a little bit later, we'll tell you when you cannot use the approximation. Okay, here's another one. 500 degrees C, equilibrium constant for H2 plus I2 yields to HI is 45. If initial concentrations of H2 and I2 are both 0.03 molar and are allowed to react at this temperature, what is the HI concentration at equilibrium? Now this is a kind of special kind of question where you can actually solve it without using the quadratic equation, even though K is a large number instead of a very, very small number. K is 45. That's a big number, and usually you would not be able to use the approximation. Let me show you how. You set up your reaction and your ICE equation. You plug in your initial values, 0.03 for the hydrogen and the I2, and 0 for the HI. And then you define X as the amount of hydrogen that reacts and the amount of iodine that reacts to form double X, 2X, for the amount of HI that forms. So at equilibrium, you've got 0.03 minus X, 0.03 minus X, and plus 2X. Now you write your mass action equation, and you set it equal to K, and you plug in your equilibrium values. It's going to be 2x squared for the HI, 0.03 minus x, and 0.03 minus x. So if you take a good squint at what we have here, really that shows you that you've got a squared term in the numerator and a squared term in the denominator. And this is what makes this really cool, because you can take the square root of both sides and get rid of the square term in the numerator and denominator. And when you do that, you get 2x divided by 0.03 minus x is equal to 6.71. So now you can easily solve for x. There's our equation, 2x divided by 0.03 minus x. So work it out algebraically, solve for x. We get x is 0.023, but again, we remember that we're asking for the what is the HI concentration, and that is defined as 2x. So we have to again double x to get our answer 0.046. So we did this even though k was a large number. Because we had both square terms in the numerator and denominator, we could take the square root of both sides of the equation, get rid of the square terms. Okay, for the reaction, COF2 forms carbon dioxide and CF4. The K is 5.8. If only COF2 is present initially at concentration of 2 molar, what's the concentration at equilibrium of COF2? Try it and come back, we'll discuss it. Okay, here we go. We write the equation down, we write the IRE setup, we start filling it in. We have 2 molar COF2 initially, we don't have any of the products. It reacts according to the stoichiometry of this reaction. So if we call COF2 2x, it's going to form X of carbon dioxide and X of CF4. So it'll be minus 2x on this side because the reaction is going toward the right, and at equilibrium we're going to have 2 minus 2x for the reactant and x for each of the products. So we set up the mass action equation, we plug in x squared at the top and 2 minus 2x squared in the denominator for the COF2. It's squared because the coefficient is 2. We set it equal to 5.80. So if we take the square root of both sides, we can avoid the quadratic equation. And when we do that, we get x divided by 2 minus 2x is equal to the square root of 5.80, which is 2.41. Therefore, solving for x, we get x equals 0.828. Now, that is not the answer to the problem because the equilibrium concentration of COF2 is 2 minus 2x. So we have to take that into account. So we write 2 minus 2 times 0.828 and we get a COF2 concentration of 0.344. Okay, now let's try this one. For the reaction, 2NOCl yields 2NO plus Cl2. Kc is 4.89 times 10 to the minus 4. We have 1 molar, 1 mole in 1 liter, 1 molar of NOCl. Don't have any products. Calculate the equilibrium concentration. So this one, I'm giving you this one because I want to show you how to test to see if you can escape the dreaded quadratic equation by doing the approximation. Because here, you're getting to the threshold of k values. If k is 10 to the minus 5 or smaller, almost always you can use the approximation if the initial concentration is large enough to warrant that approximation, and it usually is. If it gets to around 10 to the minus 4, it gets to be a little bit cuspy, right on the edge of whether the approximation will work. So with this, what we want to see is, can we use the approximation here if we have 4.89 times 10 to the minus 4 as our value of k? So we set up our ICE grid. We plug in our initial amount, 1 molar for the reagent, 0 products. The change is minus 2x following the stoichiometry of the balanced equation, minus 2x plus 2x and x. So at equilibrium, we have 1 minus 2x, 2x, and x. So our mass action equation is this. Plugging our values from our grid in, we get 2x squared times x divided by 1 minus 2x squared. Okay? if we can just get rid of that denominator as a squared term like that, and have an approximation that worked, that would be great, wouldn't it? So let's go ahead and do it. We're going to let 1 minus 2x approximately equal 1. We're going to say x is small enough so subtracting double x from 1 is practically the same as 1. Okay? And now we can easily solve the equation. 4x cubed over 1 squared equals 4.89 times 10 to the minus 4. We solve for x. 4.96 times 10 to the minus 2. So that's our value of x. Now we're going to test to see if really that's really kosher to do that approximation. Here's x. It's 4.96 times 10 to the minus 2. To test the approximation, 1 minus 2x is approximately equal to 1. What we do is we take our approximate value of the x term that we're dropping, which is 2x, because we're subtracting 2x from 1. So the value of x that we're dropping is 2 times 0.0496. And we divide that by the term that we're subtracting it from, the initial amount, 1 of molar of the NaCl. And then you multiply by 100% to get an error factor. And we get a 9.9% error with this. Well, here's the rule. If it is 5% error or bigger, you cannot use the approximation. This is almost a 10% error, and therefore we can't use the approximation. Now, if this were a different reaction where we didn't have to double x, it was like 1 minus x in a different reaction, then x would be around 5%, or even a little bit less than 5%, and we could use the approximation. It's very simple to test whether the approximation works. Whenever you're in a gray area, you don't have a k value that's really small, it's 10 to the minus 4 or bigger than that, 10 to the minus 3, 10 to the minus 2, whatever, you can test for the approximation simply by going through with the approximation, getting a value for x, and making a ratio of that value of x divided by the initial concentration, the one that you're subtracting from, times 100%. And that percent tells you whether you can use that or not. If it's bigger than 5%, you cannot use it. Okay? So here's our last one. For the reaction nickel oxide as a solid plus carbon monoxide as a gas forms nickel as a solid and carbon dioxide as a gas, the Kc is 40 at 500 K. If initially you start with 0.2 molar of carbon monoxide, 0.1 molar of carbon dioxide, what will be the equilibrium concentrations of carbon monoxide? So of course you write your mass action equation, and you want to try and do this? Do this. Turn it off. See if you can do this, okay? Go ahead, turn it off and see if you can do this. Okay, did you make the first mistake or not? Did you understand that you've got gases and solids, and it's only the gases that appear in the mass action equation? So it's the concentration of carbon dioxide divided by the concentration of carbon monoxide equals 40. The nickel oxide and nickel solid do not appear in the mass action equation. Okay, so now we can put our grid in, initial change in equilibrium, but we're only concerned with carbon monoxide and carbon dioxide. So this one, we have to do a little bit of work ahead of time because we have to know in what direction the equilibrium is going to shift. in order to make the signs of X the right signs, is it going to shift toward the product side? Is it going to shift to the reagent side? So in what direction will the reaction shift to attain equilibrium? So we have to compare Q to K, the initial value in the mass action equation, which is 0.1 for the carbon dioxide, 0.2 for the carbon monoxide. The ratio is 0.5. Therefore, Q needs to grow or increase until it equals 40. So if Q needs to get bigger, the reaction has to shift to the product side, toward the right. So now we know it's shifting to the right. And therefore, we can say X is going to be minus X for the carbon monoxide plus X for the carbon dioxide. And we can put 0.2 minus X for the carbon monoxide at equilibrium and 0.1 plus X for the carbon dioxide. So now it's a simple matter of plugging it into a mass action equation. This ratio has to equal 40. We go through and solve for X, right? We get 0.193. And again, we don't just grab onto 193 as the answer. That is the value of X, but it's asking for the equilibrium concentration of carbon monoxide. That's going to be 0.2 minus X. So that's going to be 0.2 minus 0.193, or 0.007. Okay, that's it.